Thank you very much, Alistair. So before I start the introduction, I'm required by our illustrious leader to inform you that there is no planned fire alarm test. So if the alarms go off, there are two fire exits, one out through the main door where you came in, and the second to the left out through the back door. And then we have to go, is it 72 paces towards the park or something? But 77 paces towards the park, which is the muster point. I'm assuming that Alistair will have the list to make sure that you're all not burning to death.
A metric pace or an imperial pace?
I'm going for Stardust. I've been teaching my astronomy students about Eratosthenes and how he figured out the diameter of the Earth. And apparently the debate about how accurately he got the thing depends on what you believe about what the ancient measure of a stadi is. It's a pace of some description, but nobody quite knows how long it is. Anyway. Anyway, I probably ought to do a proper introduction now. So good evening, ladies and gentlemen. Welcome to the British Interplanetary Society and our Prestige Lecture. I'm delighted to be able to introduce Professor Monica Grady this evening. Monica has a very illustrious history studying the solar system at the Natural History Museum and more latterly at the Open University. I had the good fortune to meet Monica some years ago at the Royal Astronomical Society, and then I think I was able to witness you being the Royal Institution Christmas lecturer. And if you haven't seen that, if you want to see somebody doing unspeakable things to a puppet of Albert Einstein, I think you really ought to watch that. It was very entertaining. But when I met Monica at the Royal Astronomical Society, we did a deal. I was working at Surrey Satellite Technology at the time, and Monica was at the Open University, and we did a deal that we would do reciprocal lectures, that I would go to the Open University and talk about small satellites, and Monica would come down to the University of Surrey and talk about the research that she was doing. And I did my lecture, and then somehow there was a sort of diary clash, and we had to postpone Monica's lecture, and then we kind of never got around to rearranging. So my other piece of good fortune is that, as well as being an extremely eminent scientist, Monica is blessed with a very good memory. So when we were looking for a prestige lecturer for this evening's event, I said, well, I could ask Monica. She does kind of owe me a lecture. And my good fortune is that she remembered and that she's here tonight. So, ladies and gentlemen, can I introduce Professor Monica Grady to talk about the Rosetta mission. Thank you very much, Monica.
Thank you, Stuart. And right, have you all voted? Yeah, it's another of my hobby horses. It's like it's a duty and it's a privilege. It's not a right, and we should vote. So I hope we have. I did before I came out because I wasn't sure whether I'd get back in time. So I'm glad we've all voted. Don't care how you voted, as long as you voted. Right, so the Rosetta mission, landing on a comet. This is going to be very much a personal perspective. There'll be some science in it. Probably not as much as Stuart and Alistair hoped, but there you go. This is what I'm going to do. So now then, has this got a laser pointer on? Let's see. Power on, power off. Zoom, possibly not. Never mind. Right. Okay. So why did we go to a comet anyway? Why actually the Rosetta mission? Well, one of the specific things that I'm interested in. Thank you very much. Thanks. One of the things that I'm interested in is that. The instrument that I'm involved in is that we want to look particularly at the water and carbon in the comet. All right, so these elements, carbon, hydrogen, oxygen, were present in the dust cloud from which the solar system formed. So they were present when the Earth formed 4,567 million years ago. Plenty of it there. However, as the Earth formed, it was incandescently hot. The surface of the Earth was absolutely boiling. And so a lot of these volatile materials were evaporated away. And for many, many millennia, the Earth's atmosphere was mainly made of steam. As the Earth cooled and solidified, then it retained a cooler atmosphere, and it stopped losing so many of its volatiles. one of the things that kept the Earth molten for so long was bombardment of the surface of the Earth by asteroids and comets, because as the solar system was forming, there was lots of this loose material hadn't found its final resting place. So it's quite ironic that we're now looking at the later stages of the early solar system when additional material was brought to the Earth and was retained by the Earth from asteroids and comets, bringing the volatiles to the Earth. So the first lot of volatiles were lost because of bombardment, and then the second lot of volatiles were brought to the Earth by bombardment. So the volatiles that we have now in terms of water and carbon is a mixture of indigenous material, which has always been in the dust, always been part of the Earth system, and then exogenous stuff added later on from asteroids and comets, which may or may not have changed during the early history of the solar system. So one of the reasons we want to go to a comet is to assess what the volatiles are in this particular comet and how it relates to the volatiles of other parts of the solar system, and specifically the Earth. So just a bit of revision about what asteroids and comets are. They both orbit the Sun, and going back again to this figure 4,567 million years ago, when most of the gas in this part of a nebula, most of the gas collapsed into the Sun to form the star. A lot of it then went in to form the gas and the ice giants, whereas the dust formed the terrestrial planets. Between Mars, the outermost of the terrestrial planets, and Jupiter, there is this belt called the asteroid belt. And asteroids are mainly rock and metal, and here's a picture of asteroid Matilda. And these have approximately circular orbits, so they orbit in the same plane that the Earth and the major planets orbit. Comets, in contrast, were formed, and I should say, these are parts of a planet which never formed, because although a planet should be there where the asteroid belt is, it never did, because Jupiter was already there and its gravitational pull prevented these objects from getting together to form a planet. Comets, on the other hand, formed much further out from the Sun. They formed beyond Neptune, and many hundreds of thousands of comets were then scattered way, way, way beyond Neptune to the very edges of the solar system, a place called the Oort cloud, which we've never seen, but it's a hypothetical construct. We believe it's there. And many of the comets that come in from the Oort cloud have very, very elongated elliptical orbits, and they are not within the plane of the ecliptic. So they come in from the top or the bottom or the side or whatever. And so we've got two populations of comets. We've got the ones that come from the Oort cloud, which are long period, and ones from the Kuiper belt, which is analogous to the asteroid belt, but it's a belt of objects which are mainly ice and rock rather than metal and rock. And so these are, as I say, dust and ice. And this is a picture of Halley's Comet from its perihelion passage in 1985. So one of the things we're looking at then is we're looking at a lot of the work that I do is to look at asteroids in the form of meteorites, and the cometary aspect of my work is a very complementary part of the research project. Okay, so to put the Rosetta mission into a bit of context, I'm going to move this up a bit actually so that I can get at the thing. So the Giotto mission was the first cometary mission, all right? So that was in 1986 when Comet Halley came close to the to the Sun, and this was the first image ever taken of a cometary nucleus, and it was a flyby. A fast flyby, about 600 kilometres, I think, away. And what we got, as well as the image, we got some spectroscopy which showed that the nucleus was dominated by carbon, hydrogen, oxygen and nitrogen. Now, up until then, the idea of comets was that they were icy snowballs, and so they were mainly ice, and it was sort of assumed that there'd be a rocky nucleus and that there was ice around the outside. What this mission showed was actually this is very dark, and that there didn't seem to be quite so much ice on the outside, and we've seen that now on each of the other cometary missions. So for this one, we got a picture and we got some spectroscopy. The next mission was the Stardust mission, which went to Comet Wild 2, and that was a NASA mission. This was Giotto was an ESA mission. Stardust went to Comet Wild 2, flew through the coma, and collected some of the dust from the coma in a special collector, which was full of a material called aerogel, which is a very, very light silicon and oxygen expanded, a very, very low density material. And it was hoped by capturing some of the grains of dust, we would be able to measure the composition of these dust grains, which we could. But as you can see, this is a piece, it's called a keystone, which has been taken, that's 0.5 millimetre. And so this is a track. The idea was that the material would come in and make a track shaped a bit like a carrot, and that the grain would be at the end of that track. Well, what actually happened was quite a lot often the grains exploded and you got more sort of tadpole shaped and some quite bizarre shaped tracks. And although there's been a huge amount of information come from these grains, we're by no means getting the full story, because for a start it's just dust, there were no gases, no ice, and also because of the way the grains are being trapped within the aerogel, it's very, very difficult to infer much about the carbon. So we've made big steps forward but haven't got there yet. So we've now got Rosetta, and the idea originally, the Rosetta mission was going to be a sample return mission, and so we're going to bring some material back to the Earth. But that turned out very quickly. It was going to be far too technically difficult, far too expensive, and so that was dropped relatively early on. And so it's just a mission that's gone to a comet. Now, has everybody seen this movie? Some people have seen it. Well, let's just see if we can we can watch a little bit of it now. ESA have not been very good at PR up until this mission, when they decided that actually, yes, they're going to do PR in a big way. Do many of you watch Game of Thrones? Some of you. You might recognise the gentleman in the... we're not going to watch all of it. I'm not sure where they filmed it, but I'm not sure how her dress remained white. That's Littlefinger, Peter Baelish.
Perhaps we should find you something a little less challenging.
I don't understand. I planned everything. Let me do it again.
Once upon a time.
Really?
This is a good one, I promise. What is the key to life on Earth?
Water.
Water. For a long time, the origins of water, and indeed life on our home planet, remained an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system, once thought of as messengers of...
Right, okay, so if you want to see any more of that, go to YouTube or any anything and look at Rosetta, the movie, because it's really good, okay, and it really did get people's imagination going that actually, yes, you know, ESA could do this. They could actually do some interesting stuff. They also did, let's see if I can go back out of this again. Some other things. There's this one, which I really like.
Over 10 years had passed since Rosetta and Philae launched on their exciting mission to Comet 67P Churyumov-Gerasimenko. After 3 months investigating the comet from orbit, it was time to send Philae to its surface. A long night of final preparations lay ahead of them. Finally, the moment everyone had been waiting for arrived. As the world held its breath, Rosetta moved into the exact position needed to make sure Philae would reach the landing site that scientists on Earth had picked earlier in the mission. Philae and Rosetta were sad to be going their separate ways, but excited at the same time, because this is what they had been waiting to do. Philae was away. It would take 7 hours to reach the surface, but Philae wanted to get started on his measurements right away. He could soon see the surface in incredible detail, and the moment he had been dreaming of had finally arrived. He had reached the surface of the comet. But all was not right. His harpoons did not fire. Philae realized he couldn't relax yet. He was rising from the surface again. Philae was scared he might drift off the comet completely. This was not in the plan. But eventually, he came back down again. However, as he looked around, he realized he had landed in a completely unexpected location. Philae immediately set to work on studying his new home. It took him just over 2 days to conduct all the experiments he had brought with him. After all his hard work, Philae began to feel tired, so he made sure to send all the data he had collected back to Rosetta. As the sun set over Philae's new home, he fell into a deep sleep, safe in the knowledge that he did his main job well, and that his family of comet-chasing heroes would be proud of his achievement. Who knows, perhaps one day enough sunlight would fall on his new landing site and wake him up so that he could carry on investigating this incredible world. And so, as the comet moved over closer to the sun, Rosetta prepared for the next part of her exciting adventure.
So like I say, I mean, ESA really have, you know, made a great effort with this PR stuff, which is absolutely fantastic. So now then, let's try again from the current slide. So Rosetta launched in 2004, and it took 10 years to actually get to where it was going. And the mission, though, started many, many years before 2004. The reason it took so long to get there was it didn't have enough oomph when it blasted off from Kourou to actually get to the comet. So it needed to go a couple of times around the Earth and once around Mars to actually pick up enough speed, velocity, don't know, to actually get to where it needed to be. And it did a lot of interesting science on the way. It bypassed asteroid Steins, it bypassed asteroid Lutetia, took a lot of images, spectroscopy, and most of the instruments at one time or another were awake during the actual flybys of those asteroids, and got quite a lot of stuff. So even if Rosetta had failed by the time it got to the comet, it would have probably not more than justified, but gone a long way to justifying the complexity of the actual mission. So it was launched in 2004, The instruments for the mission, though, were delivered about 2001. Now, normally, you have to deliver instruments 2 years before launch for a complex mission like this, because the individual instruments have to be integrated, because one's being built in France and one's built in Germany and one's built in the UK and whatever, and they all have to be integrated. And Ptolemy, which is the instrument that I'm involved in, was the first thing to be screwed to the base plate, all right? So it had to be delivered, then everything else could be screwed in on top of it. So it was delivered in 2001. For launch in 2003 to a comet called Virtanen. But unfortunately, the mission before Rosetta was launched, there was a problem with the Ariane spacecraft. And so the whole Ariane program went on, was paused for a year. And it looked as if the Rosetta mission might have been cancelled completely, because the complexity of the orbital dynamics getting to the comet meant that a lot of work had gone into selecting Comet Virtanen, and it looked as if there might not be another comet. But the engineers and the dynamicists and the mathematicians, you know, got out there, you know, slide rules and whatever, and managed to calculate and find that this little comet 67P Churyumov-Gerasimenko was, you know, fitted the bill. And it's like, it's a comet called what? You know, it's like it was bad enough Virtanen, which began with a W, you know, it's just like, and Brits, you know, we're just not very good at languages. So Churyumov-Gerasimenko, it's like, how do you spell it? Has it got a hyphen? Why is it called that? Well, it's called that after two astronomers, Mr. Churyumov and Mrs. Gerasimenko. And actually it was wonderful, because at the day when Philae landed, Churyumov and Gerasimenko were there, and to actually see the landing on their comet, which was really brilliant. So, you know, for a year it wasn't certain that the mission would actually be launched. But prior to that, prior to 2001, we're building the instrument Ptolemy, and that took 3 years. Prior to that, we were sort of raising the money, trying to get the money out of PPARC, trying to get the money out of the European Space Agency. Prior to that, of course, we were trying to get the mission selected. And I've got a fax, which I've recently moved offices, or office spaces within our building. And when I was packing up to move, which was the week before last, I found a fax from Colin Pillinger. Now, you all know Colin from Beagle 2. But Colin was very, very a real mover of the Rosetta mission. And this fax was to the people in the science team he was putting together, and I was one of those. And it's dated 1995, and it says, great news, we've been selected by ESA. All we've got to do now is, and then there's a whole list of things, get the money from, do this, do this, do this, do this, do this, and we're there. And it's just like, and so that was in 1995, all right? So the projects, the proposals were being put together before 1995. So this is not a 10-year project since 2004. This is more like a 30-year project. Now, the mission to Giotto was in 1985, so how many years ago is that? It's 30 years, isn't it? So, you know, it's 30 years from one Comet mission to the next Comet mission. So our next Comet mission is going to be in 2034, if we're lucky, you know. So, no, 2044, yeah, I can't add. 2044, if we're lucky. So, you know, when I give talks to school students, and I particularly like talking to 5- and 6-year-olds, I say, you're the ones who are going to have to be the people who are doing this mission, because, you know, you're those people. Anyway, so Rosetta was built on, following on from Giotto, and it was part of the European Space Agency's Cornerstone programme. And it was a fourth cornerstone. And, you know, the question is, why is it called Rosetta? You know, why? And I was just remembering with Alistair earlier on that the launch, or the press launch for the mission was actually held at the British Museum in front of the Rosetta Stone, which is about this big, you know, it's a grey slab. And the Rosetta Stone was dug up from the Nile Valley in the time of the Napoleonic Wars, and there was a a lot of tension actually between the French and the Brits at the time, not just because of the Napoleonic Wars, but because the archaeologists were fighting over, you know, who was going to do what. And at the time, nobody could read Egyptian hieroglyphics. Nobody had a clue. So they knew, you know, there were the pyramids, there was obviously this fantastic culture, but nobody had any clue until the Rosetta Stone was found. Now, the Rosetta Stone has got on it a decree on behalf of King Ptolemy V from about 200 BCE. Now, this decree is written in Greek at the bottom, and people could read ancient Greek, and it's written in something called a demotic script in the centre, which is the language of scribes. And it could be seen that actually this and this were saying the same thing. So it was assumed, oh dear, I think this isn't, no, I'll use mine. It's assumed that these two, the Demotic and the Greek, were saying the same thing. Oh no, you can't even see my arrow, never mind. So what is the hieroglyphics then? It was assumed that the hieroglyphics were saying the same thing as well. So this, for the first time, enabled, ooh, thank you very much indeed. That's a good one. Right, okay. So this enabled the translation for the first time of the cartouches, the pictograms that make up hieroglyphics. And what is actually said was this decree on behalf of King Ptolemy V said, if you worship me as a god, I'll let you keep your land, which I think is, you know, fair enough. So what this did was this illuminated the ancient historical world. It allowed historians, cultural archaeologists to understand what was going on in the ancient world, the trade, the warcraft, the civilization. And so that opened up what we could understand of the start of our own civilization. So obviously, when we wanted the name for a mission to go to a primitive object which was going to open up all of solar system history so that we could understand our origins as part of the solar system, then we go to Rosetta. Okay. And also, you'll have to forgive me, I keep saying we. You know, we did this, I didn't. Lots of other people did, I didn't, but I say we, you know, it's the royal we. So Rosetta then, following on from the Rosetta Stone, the Rosetta space mission was going to open up solar system history for us to understand. The lander on Rosetta is called Philae. All right, why is it called Philae? Well, here's the Nile Valley, here's the Aswan Dam, and here's Philae. Now, Philae is a small island in the Nile, and on Philae was a temple to Isis, who was the mother of all the Egyptian gods. A very, very famous temple. At the entrance to the temple are two obelisks, or were two obelisks. One of those obelisks is now in the grounds of Kingston Lacey, a National Trust property in Dorset. And on this, here's the Rosetta Stone again, on the Kingston Lacey obelisk are cartouches and Greek. So you've just got the Greek and the cartouches. And so understanding what was on Philae helped illuminate what was on the Rosetta Stone. So the argument is that the instruments and the information we get from the Philae lander are going to illuminate the results that we get from the Rosetta spacecraft. Okay, so it's the same sort of relationship. So coming up then to the mission itself. In January 2014, we had Wake Up Rosetta. Now this is a bit exciting because Rosetta had been in hibernation for 2.5 years. So it had been switched on to do the asteroid flybys, and then it was switched off to save power. Now, I don't know if you've got a television or a radio or something, and you switch it off, and you switch it off for 2.5 years, and you switch it on again, do you expect it to work first time? If you've got a computer, if you've got a PC, and you switch it off for 2.5 years, do you expect it to boot up first time without having to switch it on and off? No, you don't. You know, it's like, wow. Rosetta woke up straight away, absolutely on time, you know, no problems. It was just brilliant. It was a miracle, you know, and so it's like, hey, just fantastic. Rosetta woke up, brilliant. And so between January and June, there were lots of discussions about where Philae was going to land. And there was an assumption that it was going to be landing on something that was approximately spherical. Now, it's very, very important to know the shape of the comet, because you've got to know the mass of the comet, because it's known it was small. It's only about 5 miles or so across. It's got no gravity, hardly any gravity of its own. Things can land on the moon and Mars because they've got gravity. We stay stuck on the Earth because of our gravity. So something, if it's going to actually stay on the surface of a very small body, you've got to know what the gravitational attraction between the two bodies is. And so you have to know the mass. Now, they could make assumptions about density. They could make an assumption or make a calculation about its width, and assuming it was approximately spherical, they could make an idea about what its mass was. And so that was great. And so my colleagues at the Open University were taking part in telecoms when they had an image of the comet, first of all, which was 1 pixel across. And then they had an image which was 6 pixels across. And they were doing landing site selection workshops, right, on something that was 1 pixel across, where you couldn't see any shading in the pixel. It's like, okay, how about that bit? You know, it just sort of didn't mean very much. We got to July, and this was one of the first images that was released of what shape the comet was. And it was horrifying, because suddenly it's not, you know, spherical. And a lot of the scientists and the engineers went, oh, duck, you know, what are we going to do about this? Because, first of all, it's got 2 lobes, and we don't know whether the lobes are 2 things that have come together and stuck together, or are they one thing that's been carved out by impacts. So we don't know. Are they 2 things that are the same density, the same, made of the same material, or not? And so at this stage, right, okay, I've got any engineers in the room? Yeah, a few people sort of, yeah, okay. At this stage, the engineers, who are, as a race, risk averse. Yeah, right. Engineers tend to be risk averse. Scientists tend to be gung ho. All right, and so it's like, yeah, go for it. Engineers, he can't. And it's just like it's a clash of 2 cultures, and it's absolutely crucial that those 2 communities come together and have a meeting of minds, because you're just not going to get anywhere. You've got to have the gung-ho scientists saying, yes, we've got to do this. You've got to have the engineers saying, well, you can't. And then the engineers say, well, actually, we could try this. And the scientists say, well, how about if you... And, you know, eventually there is a meeting of minds. So the engineers sort of said, well, there's no way we can land on this. And at the time, the scientists were saying, oh no, there's no way we're going to be able to land on this. So, you know, it's like really difficult. And especially as we got closer and saw, you know, got even more terrifying images of what it was like. How are you going to land something the size of a washing machine on this when you don't know, you know, what its density is, you don't know what the gravitational attraction is. So all the shape models had to be thrown out of the window and started again. And it was just like, oh, there's not going to be time. Yes, there is. Yes, there is. You know, you've got good computers. Get on with it. Oh, all right then. So we'd got these images, and simultaneously we'd got an image. This is from a telescope on the Earth of the comet at the same time as these were taken. I think this is August actually, so a bit earlier than these were taken. And what you can see is this is a very traditional looking image of a comet, and you can see bright nucleus and quite an extensive tail. Now we weren't you don't get that impression when you're looking at these close-up images, but when you see this sort of image, you realise that actually the comet is active, which gives you an extra dimension of concern, because if you've got a lot of dust here, the way the Rosetta spacecraft is manoeuvring, it has a star tracker to navigate by. Now, if you've got lots and lots of dust, they impersonate stars, impersonate a background of stars. They're very bright, and so it confuses the navigation cameras. So again, there was concern that the comet might have been more active than people had anticipated. Just as a side, you know, as I dig at any astronomers who are here, this image was taken by a very, very fancy telescope on the Earth in Chile. It's a very large telescope, and it's called the VLT, which stands for Very Large Telescope, which, you know, when you think of the effort that space scientists go into in sort of inventing wonderful names for their space mission, to call something called to call a very large telescope the VLT, it's just like, you know, where's the imagination in that? You know what they're calling the next one? ELT, Extremely Large Telescope. I don't know. Okay, so we got to this stage. We got to a stage when the engineers had said, right, actually, yes, we can land on it. It's going to be a bit, you know, not quite as straightforward as we thought. We need to actually decide where we're going to land. And so the workshops, now they've got some, you know, real meat to work with, selected 10 places where they thought the Philae could land, and landing site J was selected, and it was named Agilkia, and the landing was scheduled for November the 12th. Now, ESA had, again, you know, as part of this wonderful PR machine that they were doing, they had a competition for people to write in and name the landing site, and I got a certificate to acknowledge my proposal of Agilkia as the name of the landing site of Rosetta's lander. So I named it. So it's like, yes, along with about 500 other people. Yeah, it's like, but never mind, I got my certificate, which, 200 others. So that was good, So why Agilkia? Why did I choose this name, and why did so many other people choose the name? Well, let's go back to Philae here, just south of the Aswan Dam. Now, when the ancient Egyptians built this wonderful temple on the island of Philae was secure. But then the more modern Egyptians built the Aswan Dam, which changed the water levels of the Nile. And Philae, the island, started to flood regularly. And so this ancient temple was being washed away. And so because this is a site of cultural heritage, a UNESCO World Heritage Site, UNESCO organised for this temple to be moved stone by stone and rebuilt on an island next to, a bit further upstream, a bit further closer to the banks, called Agilkia. And so Agilkia became a safe haven for the Philae temple. And so the landing site for Philae, the safe haven, was Agilkia. And it would have been marvellous if only Philae had actually landed there. You know, so there's a bit of a shame. All right, so let's wind forward then. So we've decided where it's going to go. We've got to a stage now where everything's ready, and it is the 14th of November, 2014. And there are people out in Darmstadt, which is where the ESA's control centre was. And there were people out at Cologne, which is where ESA's control centre was. Now you immediately see there's a bit of a problem there. We've got two ESA control centres. One was mission control and one's mission operations. Okay, and I could never remember which one was at Darmstadt and which one's at Cologne. But I was at Darmstadt, and Darmstadt was where the well, I say great and famous. Oh, and I was there. What I mean was there were people like, the science ministers were there. David Parker was there from UK Space Agency. The mayor of Darmstadt was there. The director general of ESA was there. All the world's journalists were there. And the principal investigators of all the instruments were there. So Jean-Pierre Biebering, who's the leader of Philae, was there. Ian Wright, who's my husband and the principal investigator of the Ptolemy instrument, he was there. I'd been invited invited, as I'm one of the science advisors for Ptolemy, so I was invited along as well. So that's all in Darmstadt. In Cologne, which is, I don't know, 100 miles or 100 kilometres away, geography is not my strong point, was where the rest of all the mission teams were. So Ian, the PI, was in Darmstadt. The other 5 members of his team were in Cologne. And that's where all the other team members were. And they were in direct contact with the people who were actually talking directly to Rosetta. So information was going first to Cologne and then coming to Darmstadt. And so we'd had a bit of a scare late the previous night when there was this rumour that the thruster on top of Philae wasn't working. So this was a rocket motor which was going to push Philae down. But hey, there were two other mechanisms which were going to make sure that Philae landed. So, we don't know about the thruster, but there's 2 others. We don't need to worry about that so much. All systems were declared nominal, which is the most exciting that an engineer can come up with in terms of things are working brilliantly, all right? Systems are nominal at 8 o'clock in the morning. So all systems go for the release of Philae at 10 o'clock. And this is what happened. And so everybody was herded into this big room in Darmstadt, and we saw the final pictures of Philae leaving the Rosetta mothership. There was none of that hugging with, like we saw in the cartoon, but that's what it felt like. You really felt like you were saying goodbye to your only child. Going off into the, going to explore the unknown. And so then we'd got to wait until 5 o'clock. We'd got to wait until 2 minutes past 5 to actually get the signal to see the thing had landed. So we've got 7 hours. All right. Now, the most NASA could do was 7 minutes of terror when Curiosity landed. All right. ESA, we don't do things by halves. We have 7 hours of terror. And, what are we going to do for 7 hours of terror? Well, we're going to watch Ambition the movie, like on the hour, every hour, to stir us all up and make us feel, really, really great about being part of this wonderful space team. The journalists were interviewing anybody they could get to stand still long enough, and then the journalists interviewed each other, and we interviewed the journalists, and we interviewed each other. And it was a great feeling. I did 10 radio interviews in an hour. I did something called World Service News, which is where local news services bid for your time, and they get 3 minutes of your time. So I did a 3-minute interview and then had 2 minutes, a 3-minute interview and then 2 minutes. I did Radio Jersey, Radio Leeds, Radio Stoke, Radio, Southampton, all these local radios, and they all ask the same question, and so it's really easy, but, it was absolutely exhausting. So all this is going on, and then it gets to about sort of 4 o'clock, and then the journalists who don't understand engineering, they're getting twitchy. Shouldn't it have landed by now? It's like, no, it's going to land at 2 minutes past 5. Well, shouldn't we have heard something by now? No, it's going to land at 2 minutes past 5. And it's like, well, how can you be sure? Well, we've got gravity, we've got orbital dynamics, we know these things. If people say it's going to land at 2 minutes past 5, it's either going to land at 2 minutes past 5 or it's not going to land at all. It's not going to land at 4 minutes past 5 or 10 to 5. So we were entertained episodically by having more images, and so we got this image. One of the first images actually from Philae, where you can see one of its legs, and it's like, oh right, actually fantastic. Hey, yeah, should we know, this, that, and the other? And it's like, right, okay, no. And you keep saying, we will hear. And so we were all in this room, and we were waiting, and you could see projected on a big screen. There was the engineers in the mission control room, and you could see, by this time, all the principal investigators had gone off into another room, so I wasn't with Ian. They'd gone off into another room, not exactly certain why. And we'd got this on the screen. We could see the people in mission control, and they'd be sort of walking around, and one of them would look at the screen, another would look at the screen, and it's just like, this went on, and it seemed to just go on and on and on and on. All right, and so now I've got something else to show. which is awful. Oh, you're not seeing it again? Well, you can hear it. You don't need to see it. You can hear it. All right.
Sorry, David. Sorry, I didn't mean to hug you like that, but I'm so excited.
Right. Right, okay, I can't cope with that. You know, it's just too embarrassing. All right, yeah. So, right. So let's go back to where I was. So, what I was just trying to show was that. Let's get rid of all of those. Do you want to close those two tabs? Close those tabs. Let's close all those tabs. It was an absolute relief of tension. Okay, it was called, this is a moving and ecstatic reaction, it says. And it's like, it wasn't just moving and ecstatic, it was just amazing. And I got lots of emails from, we're still not there, are we? From the current slide, waiting for the landing signal. Right, okay. I got lots and lots of texts after that. I got one particular one from my niece, Beth, which said, "You are just the world's most embarrassing aunt ever." And I got one from my younger sister, Ruth, which just simply said, "Get a new bra." And it's just like, all right, thanks, family. You know, I'm glad you're with me. So it was just absolutely, you know, it was just wonderful, absolutely wonderful. The only thing that took it away was the fact that Ian wasn't with me. He was in another room, all right? But about 10 minutes later, he came down. I gave him a big hug, and we took a selfie together, big smiles. I found him because we were all tweeting. It's like, I was hugging him. I was like, "Oh, you must be so happy. You know, you must be so happy." And he just went, "It's all gone tits up. Keep smiling." And it's just like, what do you mean? Because the people you saw in the Rosetta, in the cartoon, what Feli was doing. He had a hammer. Do you remember? He hit something, and then he hit it a second time, and it bent the hammer, and he went. And that actually is what happened. No, that's the second thing that happened. But the team, the MUPUS team, were going to actually try to push down into the comet to measure the thermal conductivity. They got the signal that yes, it had landed, and then they lost the signal straight away. And then all the other teams, which were, you know, monitoring other things, were like, "Yes, it's landed. Hey, fantastic!" It's not there anymore. And so they knew straight away that it had bounced. Now, we weren't told about this until about 2.5 hours later. Okay, so we'd by this time, the people were saying, right, okay, so there were rumours sweeping the place, you know, like rumour central. And this image was released. Now, these say 1,500 hours. So what you've got to remember is that this is UT, and the 1,700 hours was because it was at Central European time. So at 1514, there was a picture that you could actually see Feli. At 1519, it was coming in. It looks as if it's drifting across the surface. Here it is. They reckoned this was taken at 1543, which is 1643. All right, 4:45. But actually, it takes 20 minutes for the signal to get back. So bang on time, it touched down. And they reckon you can see where the 3 feet touched down and disturbed a bit of dust, because that was taken on the pass before. And so they reckon that actually it's landed over here, where it should have landed over here. So it landed bang on time and then bounced. And they think it bounced huge distance, came down, and then did bounce 3 or 4 times, possibly tumbling, but we don't know. So it was like euphoria, not euphoria, limited euphoria. Okay, so it was clear, though, that the scientists at Cologne were getting better information because they were in direct contact with their own instruments. And because Ian was with me, I was getting that better information as well. So we knew that it actually had touched down at least twice more and then had come to a halt. So that was good. What we didn't know, and still don't know, is what orientation it's come down in, and we still don't know where it actually is. But the next day, it was clear that the thruster hadn't worked, the harpoon, which was going to fire in and sort of act as an anchor, hadn't worked, and then the spikes on the 3 legs also hadn't worked. So you've got 3 fail-safe devices. You know, even your most risk-averse engineer would say a backup of a backup. You know, it should be good enough. We don't know why they failed. No idea. Or at least, I mean, somebody might know, but I don't know. But there was concern, you know, is any science going to get done? But actually, science started as soon as Philae settled. There was a battery on there which was going to last for 70 hours. That was the main battery. And then the idea was that the secondary batteries would kick in. The solar-powered batteries would kick in. But the science planning that had gone on was such that practically all of the science could be achieved in that first 70-hour period. So the instrument that I'm involved with, Ptolemy, is something that can sniff and taste. Okay, so it sniffs. So if you sniff, you know, you're detecting molecules when you sniff. And so this is what it was doing. It was detecting molecules. The taste mode, the idea was the drill on the lander would drill a solid sample, put ice and dust into an oven on Ptolemy, which would be heated, and then the volatiles would go into the system, which is a combination of a gas chromatography system with a mass spectrometer. So it's going to look at things separated by molecular mass, and also by isotopes, so looking at deuterium, hydrogen, looking at carbon-13, carbon-12. So we got lots of good results, none of which I'm going to tell you in detail because they're still, well, partly they're still being worked on, and partly they've been written up and they're under embargo at the moment. But so I'll show you some limited, well, no, I'm not going to show you any images of any results actually, but this is the prototype of the instrument that we sent to the Comet, and this is Sasha Vakovsky, who is standing up and who is 6 foot tall, okay, for scale. So as you can see, it's quite big. It's made of angle iron with lots and lots of valves, taps, lots and lots of wire. So this is the prototype. So after a little bit of, you know, head scratching and a bit of engineering, it was brought down to something this size. So this is Andrew Morse, who is the Deputy Principal Investigator, who is, well, he's also 6 foot tall, but he's sitting down. And so this is our shoebox size. These are 2 tanks with helium, and the helium flushes the gas into the system. And so all this wire, that's all the gubbins that you could see on the other system. So the first announcement we made of the results was this at the Lunar and Planetary Science Conference in March earlier this year. And this conference has got ideas above its station in terms of writing a short abstract. So you write to make a pitch for a talk, you have to write a 2-page abstract. But you have to make an abstract of your abstract, and they like you to do that in the style of a haiku. So this was Ian's haiku. Land bounce mass spectra. Land bounce land. Stop holding breath. Loads of organics. So that's his haiku. I haven't counted the syllables, but he assures me it is of the right structure. So that's the announcement, and this is from the main thing. Although we landed away from where we're supposed to have made contact, we recorded a demonstrable signal that is far in excess of any background and clearly shows the presence of a diverse array of compounds. Right. So for Ian, you know, Ian's an engineer at heart, you know, and so for him, a demonstrable signal, you know, he could say it's a demonstrable signal. Any of us, the rest of us would say, you know, it's like staring you in the face. It's like it's there definitely. So we've got a lot of numbers that we're actually dealing with at the moment, and there's a bit of discussion about some of the interpretation of this diverse array of compounds. Ian and the rest of his team think there are bridges between the organics with oxygen in them. I think it's sulfur and nitrogen. So we're having a bit of a debate over the tea table at the moment, but you know, so we'll get there eventually. So we've definitely got lots and lots of organics. Now the problem is that because the drill couldn't drill, because Philae probably landed on its side rather than landing like that, it landed like that. And so the drill couldn't drill the ice. And so we haven't been able to analyse any ice. We've analysed the dust and we've analysed gas. So we're trying to make sense of the numbers that we've got to try and get some deuterium-hydrogen ratios. But we're not certain that we can actually deconvolute those at the moment, but we're still working on it. Okay, so that's as much as I'm going to tell you about our data. I've got a few more slides which are pictures of the comet. This is a picture of one of the craters, and here it's been enhanced, and I hope you can see that there are jets coming out of the comet. Now, what none of us, I think, realise when we look at pictures like this, and these are some of the pictures from the OSIRIS camera, which is the main camera for taking scientific images as opposed to the navigation camera images, is how black the surface is, okay? So it is black. I mean, there's no ice as far as we can see on the surface. It's black, it's in some ways it's dusty, but in some ways it's very, very hard. I made reference to the hammer bending. Now, the thermal conductivity probe, which was the first thing that showed that Philae had landed and then bounced off, once Philae had settled, it was supposed to just push itself into the soil to get an idea of what the surface conductivity was. But it couldn't get through, and so it started pushing more forcefully, and in the end it was trying to hammer its way into, to the extent that they thought it was actually accidentally trying to hammer itself into one of the legs rather than into the soil. But then it did go through, and they got thermal conductivity measurements. So the surface of the comet is really hard in some places, really hard. Has it been indurated because the dust which was bound up in ice has settled back down and it's got stuck together through cosmic radiation? We don't know. The thought was that any layers that had been altered by cosmic radiation would have been blown off, in a previous passage, because it comes around every 6 years or so. So, there was a thought that the surface would be freshened, but it doesn't seem as if that's the case. There are amazing features like this. This is the neck of the comet. You've got this big crevasse. Now, is this showing that this is breaking up, or is it showing that it's come together? There's interpretation because of the way it goes over this boulder here, and it moves, and then it seems to get lost. So that's one thing. Here's a different view of the one of the features near the neck, and to me this is amazing. I mean, this could be a valley on the Earth. This could be in the Lake District. This could be a U-shaped valley that's been caused by glaciers. It's caused by the flow of ice. Has it been caused by the same way? The dust we saw, a lot of these boulders have wind tails of dust, but there is no wind at all. What it is, it's dust coming off in a jet and then being sorted by size as it falls back down again. So some really, really amazing images. This was the closest image, which was taken on the 14th of February, a flyby 7 kilometres above the surface. And there wasn't any real hope that it would be able to find Philae. They found Philae a dozen times, and then they realised that, oh no, it's not Philae, it's just something else. So it was going to come down to, to get some really close-up images of the surface from the navigation cameras. What it actually found was that the activity of the comet was such that it got a bit confused, and so they lost control of Rosetta. The control people lost control of Rosetta for a couple of hours. And then about 2 weeks ago, maybe 3 weeks ago, came close again. Not as close as 7 kilometres. I think it was 20 or 30 kilometres. But the comet has now become so active that even when it came down to that close approach, there was so much dust coming off that Rosetta completely lost contact with the Earth. The high gain antenna swung around, so it was no longer in contact with the Earth. There was so much dust coming off. They actually lost contact with Rosetta for about 24 hours before they got back in contact. And so now I think they're about 100 kilometres away, and it's very unlikely that they will come closer than that. And so what this actually means is, as we approach perihelion, which will take place in August, the Rosetta spacecraft is going to be much further away from the cometary nucleus than actually a lot of the orbiter mission people would really like. So the science they're getting, they've got good science so far, but they're going to be a bit more restricted as we come past the sun. But once we've come round the other side, they'll start taking data again. What we've got to do, though, is find out what we need to know is Philae going to wake up? As we come closer to the sun and the sunlight strengthens and there's more material blowing off, is Philae going to wake up? Who knows? We don't know. If Philae hasn't woken up by August, by perihelion, it's unlikely that we're going to get anything else out of Philae. But, you have to keep on hoping. You have to sort of keep the faith. And we're really, really hoping. And Rosetta is listening. It's not like it's gone so far away. I mean, the signal from Philae, it will pick up the signal. And so we're hoping that Philae is in such a position that the solar panels will pick up enough power to actually warm Philae up, because Philae will be frozen, warm Philae up and actually recharge the solar batteries. But we don't know. So this is one of the images that was published the week before last. Can you see the jet? So, duck farts. Not me. That would never occur to me. So this is what we're going along at the moment. The Rosetta mission is continuing. It's riding alongside the comet. Closest approach, I say, is in August. We're still listening to Philae. And we're getting on and interpreting and understanding the results. And it's been a really interesting ride. And, what we're doing as well as trying to understand the results and write papers and talk to people about it and stuff, is trying to gear ourselves up to writing some proposals for another mission to a comet, which is like, I don't know whether I can take the stress. Thanks very much.
Thank you very much, Monica. That was great. Does anybody have any questions they'd like to ask? I can see one there.
Wait for the microphone to come over.
Oh, sure.
Thanks. A couple of quick questions. How far is Rosetta going to follow the comet after perihelion? And does Philae have any kind of form of writing mechanism on it if, for example, it wakes up that might allow you to potentially start drilling, or is that just something that was practically impossible?
Writing. I was thinking, writing. So what's it do writing? Of course it's not going to write. Right, okay. So Rosetta is going to keep going as much as it can. And so the nominal mission end is December this year, so it'll be way past perihelion. So the whole idea of the mission was it stayed with the Rosetta as the comet became active and then as the activity decayed. But there is a suggestion that the mission might be extended for another year. Whether that will happen or not, I don't know. But Rosetta will keep following the comet for as long as it can. As far as Philae righting itself is concerned, it hasn't got a righting mechanism on it, no. There are certain things that might be tried. So the solar panels can rotate a little bit. So it's a possibility that trying to rotate the panels might work. We don't know, though, if a jet goes off to the side, it might be pushed over, or, it might be pushed over the other way. We don't know. But it hasn't actually got anything to actually right itself, no. But if the mission people do decide to try and right it, they will get as much science. If it wakes up, they'll get as much science as they can before they try writing it for the drill.
If I may, I've got the microphone, sorry. Yeah, fascinating that. In fact, Simon Barraclough, when he was here a couple of weeks ago, did point out that more fuel had been used in some of the manoeuvres on Rosetta. Will that limit the amount of time that Rosetta stays with the comet or not?
Yes.
And I understand that there may be some damage to solar arrays from these jets.
Yes, yeah. So there's two things there. I mean, the actual amount of fuel is the limiting factor, and so because it had to do more manoeuvring than anticipated, it's going to not last as long. And it's got solar panels to keep it going, and obviously the more damage to the panels, the less efficiently they work. But so that's why Rosetta has retreated to further away from the comet, to limit the damage to the solar arrays and to make sure that it doesn't lose the star tracker again. Yeah. Can you wait for the microphone?
Oh, sorry.
Yeah.
Oh, it's all right. But referring to these comets, are mainly composed of ice. How initially was the ice formed in the comets itself?
Well, because if you go back to the cloud of gas and dust that the whole solar system was made from, there was a lot of water in that gas and dust, and these comets formed beyond the snow line. They formed far enough away from the sun that that water condensed as ice. So it's primordial water, and this is one of the reasons why we're interested in seeing how much of that primordial water has come from comets, or how much of that primordial water is on Earth that has come from comets.
Would it require, though, the elements of hydrogen and oxygen to be present to be combined to form the water?
Oh yeah, but that was all there.
Yeah, that's interesting.
All the elements that we have on the Earth were present in that cloud of gas and dust. So they're all present in comets and asteroids and Mercury and Jupiter. They're all there. There's no elements in comets that aren't on the Earth.
You explained where some of your names came from. Is there a particularly convoluted reason for the name Ptolemy for your instrument?
Oh yeah, well, because it was King Ptolemy V whose decree was on the Rosetta Stone. So that's why. Now, there's also Modulus. Now, I can never remember what the relationship is between Ptolemy and Modulus, but the Ptolemy is the instrument, the whole package, and Modulus is the name of the detector. And modulus is short for method of determining the something, and I can't remember what the EULUS stands for. You have to ask Ian. But modulus is named after Thomas Young, as in Young's modulus, and Thomas Young was the scientist who worked on trying to understand the hieroglyphics on the Rosetta Stone, and was in conflict with Champollion, who was the French person doing that.
Right. I've got one more question, sorry.
Go on.
Before I let go of this. You say the harpoons didn't work, but the photograph shows 3 indentations where the feet touched down.
Yeah.
Could it just be it was thick dust and the harpoons didn't have anything to grab to?
Could be, yes, absolutely.
Right.
Yeah.
Okay.
I think there's one there.
There was a theory, so I understand, that the Earth's oceans were formed by water from comets and asteroids, and rumour has it, if I can put it that way, that after the Rosetta mission, that theory was discounted. Would you care to comment on that?
Yeah, that was data from the Comet instrument, which is on the Rosetta orbiter, on the Rosetta spacecraft, which was looking at the elemental abundances of the dust and gas, and that was published in Science in January, in a special issue of Science with a lot of the Rosetta data. Now, what's interesting about that is the instrument published the deuterium-hydrogen ratio of the gas that was coming from the comet, and these were data that were acquired in August, when Rosetta was still quite some way from the comet. It was the stuff that was outgassing the most from the comet, and so Rosetta Comet has got a lot more data since then. The problem with the data they got showed that the deuterium-hydrogen ratio was very similar to that of Jupiter, I think. Very similar to that of a couple of other comets that had been measured spectroscopically from the Earth. And it was different from the isotopic composition of Jupiter, which is taken to represent the primordial solar nebula as well as we can at the moment, and very different from the water on the Earth. And it didn't seem as if it could be made by mixing. It couldn't be that you take this and add it to that and get that sort of thing. And so the conclusion that the team made was that actually there was no cometary water on the Earth. However, as I say, this was very early outgassing from the comet, and I think it was a bit premature. All right, so I don't discount it, but I don't think it's telling the full story.
I was thinking about the dust that's coming off this comet. I presume it had been coming off for about 4 or 5 billion years, and the comet presumably is getting smaller and smaller as time goes on. Mm-hmm. Would you like to comment on that and explain that where this dust is going? You know, what's actually happening with the dust, and that presumably happens with all comets.
Mm-hmm. Mm-hmm. Yeah. Well, the solar system's full of dust. It's one of the dustiest places you'll ever find, and we saw that from the Ulysses measurements from many years ago, when you could see you got an idea of the zodiacal dust and actually how much dust there was in interplanetary space. A lot of the dust eventually gets swept up in the sun, which is where most of the comets end up. I think we really do underestimate how many comets we've got coming through the solar system. It's quite salutary if you look at some of the images from some of the solar orbiting spacecraft, and you can see some great pictures from Stereo, for instance, and from the SOHO missions, where you can see sort of comets just like, you know, falling into the sun all the time. And so a lot of that dust gets swept up, and gradually by a very weak gravitational Poynting Robertson drag eventually ends up in the sun. Some of it comes through the Earth's atmosphere as shooting stars. So and so we know how much there is, or approximately 60,000 tons accretes to the Earth every year from comets and asteroids, and the same amount relatively on all the planets. Jupiter hoovers up a lot, Saturn hoovers up a lot. So
you've got this wonderfully shaped object with marvellous dynamics, rotational dynamics. But has anyone noticed whether the axis of rotation is changing because of the dust emission? Is this actually having any effect, or are the only changes in the axis of rotation just simply the orbital ones as this comet goes round the sun?
It's tumbling. I mean, and although there are plots which are showing that there is a certain amount of change, there hasn't been enough change yet to actually, for it to make a gross dynamical difference. Okay.
So you talked about the comet being black.
Yeah.
Could you say, first of all, how black is it in everyday objects, and then snow and ice is generally lighter than black. So has the blackness kind of, I presume it's carbon, but has it come from collecting it up through space dust, or is it more a case of it's been in there and then as the comet shrinks, it kind of more of it's on the surface?
Right. I've described it in the way that Baldrick might describe something, or Lord Blackadder. It's blacker than the blackest black thing that you can think of. Okay, it's that black. The closest black, it's matte black, and the closest black thing is printer ink. So if you open a cartridge of printer ink and you've got that really black, fluffy stuff, it's that sort of blackness, but not that sort of fluffiness. We thought maybe it was, but the mucus, showing it's indurated. Now, as these comets travel around, they're bombarded by cosmic radiation. And what the cosmic radiation does, it does the same thing as it does to your skin. It burns it, all right? And it transforms molecules and carbonizes things, all right? So you go from a sort of fluffy aggregate which might have lots of dangling bonds and bits of oxygen and sulfur and nitrogen and lots of hydrogen, to something which is much more graphitic, much more condensed. And there's a thought that there might be more of that on the surface than imagined. Now, as I think I said briefly in answer to somebody else's question, that is surprising because cosmic radiation has to be, it's been going on for millions of years, obviously, while the comet's been travelling in space. But each time it comes close to the solar system, close to the sun, more of that surface material blasts away. And so there was an assumption that it would be relatively fresh. When Halley's Comet came close, it was such a surprise that it was so dark. Same with Comet Wild 2 from the Stardust thing. It's these things have got albedos which are much, much closer to the naught than 1. So 1 is an albedo of ice. It reflects everything, albedo of a mirror. So an albedo of 0.05 or whatever, it's nothing. It's like very, very absorbent, and it's a bit mysterious. But yeah, it's black.
I need to hand the microphone to Alistair in just a moment, but before I do, perhaps I could just ask one quick question. I did see some discussion as to whether the two elements of the nucleus might at some point split apart and give Rosetta a bit of a quandary as to which one to follow. Do you think that's at all likely or not?
Well, there's a lot of discussion as to whether, even before we knew that it was the shape it was, when it was known that it was going to be Comet 67P that was going to be the target, and this is its size, it's like, crikey, is it actually going to make it all the way into the solar system before breaking up? Because a lot of comets do break up. So it wouldn't be a surprise if it broke up. I think it would be very interesting if it broke up. We'd get some great images for a very, very short period of time. I don't know. I don't know the likelihood of it breaking up. I really don't know. I don't think anybody knows until it actually happens. My nightmare, not my nightmare, but wouldn't it be sad though if a comet went round the sun and went all the way out, and Rosetta died, because that's what Rosetta did, and then in 6 years' time the comet comes closer again, and then another 6 years it comes closer, and then on about its fourth pass, in 25 years' time, Philae wakes up, it's like, hello, I'm here, and there's nobody there to listen.
That would be
so
sad.
wouldn't that be sad? But we've got no idea.
Well, thank you very much. That was excellent, and we learned an awful lot from that. I have to add my bit, if I may, because I was the PR director of Astrium at the time, and helped run all the news events, etc. And I had to learn all about Rosetta and all the other stories that went with it. But then I had the most exciting radio interview. You did probably a lot of them, but I just did one. because I had a film crew actually down where we were watching the launch from. And I got this sudden phone call at about sort of 10 minutes before we were supposed to launch. And this guy from Prague Radio rang me up and said, "Mr. Scott, we are about to do an interview with you. We would like to ask you some questions." And they said, "You must be very excited by this mission." And I said, "Yes." And he said, "You must be wondering if you're going to find life on this other object." And I said, "Yes." And he said, "I expect you are getting ready for the launch." And I said, "Yes." And he suddenly said, "Thank you, Mr. Scott. That's the end of the interview." And all I said was, "Yes, yes, yes." So I'm afraid it was not, I thought this was the warm-up and not the real thing. So that was tremendous. Thank you. And I think it's joined us up now with the previous talk where we actually wondered whether Rosetta would actually get there. And to hear that it actually did, and it actually did its job, I think it was. And it was also fascinating to see some of the instruments that you produced at the Open University, because I recognise a lot of Beagle instruments amongst that lot,
yes,
the mass
yes,
spectrometer.
yeah.
So massive connections with Colin Pillinger there, and of course Ian. So that was fantastic. Now what I'd like to do is present you quickly, and I think I've got to hand this back, is present you with a couple of little items here, if I may. There's the story of the British Interplanetary Society.
Oh, how lovely. Thank you very much
Just
indeed.
Bedtime reading.
Yeah, lovely. Thank
but
you.
I'd also like to present you, if I can open it, with this little... This is a little comet.
Oh, that's lovely.
This was the initial logo of
how
the
lovely.
BIS, but it
Thank
is
you.
for all your work on your cometary
Oh,
exploration.
how lovely. Thank you so much.
Well, thank you.
Thank you very much indeed. Thank you. That's lovely. Thank you. Thank you.
Now, before we all rush off to the pub, please remember that we've got another event happening, 19th of May. We've got Dr. Daniela Petrova coming to do space medicine. And then we've also got, on the 21st of May, if you've all bought your tickets, we're actually going to all get along to watch, or to listen to Alexei Leonov tell us about his very first spacewalk. And that's at the Science Museum. You have to go through the website and book, because we've got about 400 seats in the IMAX at the Science Museum. And that's, I think, starting about 6:30 in the evening. So hope to see you all there. Thank you very much. Thank you.